In this video, we're going to work example problems where we solve rational equations. So first, let's remind ourselves what a rational equation is. The formal mathematical definition is that a rational equation is an equation to where each term is a rational term or a rational expression. However, I gave you a more informal definition that I think is going to be really helpful for non-math majors in terms of categorizing equations, because the formal definition means that even a linear equation like this is a rational equation, technically. Because, so rational equation, each term is a rational expression. Well, we know a rational expression is a ratio of polynomials. Well, okay, the minus 5 here, we've got a 0th degree polynomial with leading coefficient minus 5 in the numerator, and a 0th degree polynomial term here with leading coefficient 1 in the denominator, right? So each term is a rational expression, but the more informal definition that I gave was that we're going to look at a rational equation as if there's just one term in the entire equation to where there's a variable in the denominator raised to a whole number power. So to the first, second, third, fourth, just one variable somewhere in the denominator of a fraction that's raised to a whole number power, then we're going to call that a rational equation. Okay. Now, but also note that we call this rational, right? However, if you find a radical term somewhere, well, then this is as far as naming convention of the equation or the expression, this is going to take precedence. So now we'd call this, even though there is a rational term, we'd call this a radical equation. In the same way that if we had here's a linear term or a polynomial term, but if you have, do we call this a linear equation? Well, no, because this is going to take precedence. We'd call this rational equation because of this term. And so, but also in the same way, what's going to take precedence over the radical term would be a logarithm, or an exponential. So if we had an exponential, now we're going to call this an exponential equation. And then if we had a logarithm, this is going to take precedence. Now we call this a logarithmic equation. That's going to be the general way we're going to approach naming equations in general. Okay, so now how do we solve rational equations? Well, it's the same general procedure that we talked about with linear equations. We're going to be, we want to simplify both sides of the equation, as well as and kind of grouped with simplifying is clearing fractions and then simplifying from there. And then we want to use the properties of equality of equations, adding and subtracting things to both sides, multiplying things and dividing things by both sides, to isolate the variables on one side and the constants on the other until we can get all the way to having a variable with coefficient 1 on the left with some constants on the right. So where we can easily read off the solutions, because we'll still have an equivalent equation here to the original equation. And so what we saw was that when it came to linear equations where there were fractions, what we did was, you didn't have to do this, but the general way that, the way that I like to do it, and a lot of people do it, is when we had a linear equation with fractions, you multiplied the entire equation by the least common denominator of all the fractions to clear the fractions. That's where you started. Well, we're going to do that same procedure with a rational equation. We want to start by clearing the fractions. Yeah, and also note that the rational equations we're going to be solving in this video that we're talking about in this section are just the variables are just raised and the denominators are just raised to the first power. But note that this would still be a rational equation. This would still be a rational equation. But we haven't talked about working with, solving equations with powers on variables greater than 1 yet, so we're not working with that. We'll work with rational equations. We'll solve rational equations later like this, but not in this section. Okay, but again, we're going to start to solve a rational equation, we start by multiplying the entire equation by the least common denominator of all the fractions. So in this case, we can see that would be 2y. Okay, now, but this is a little bit different than what we did with linear equations, because with linear equations, we didn't have any variables in the denominators, so we were always multiplying the entire equation by a constant. Here we're multiplying by a variable expression. And the reason why this is different is because, remember, with properties of equality, when you're multiplying something or dividing something by both sides, well, you can't multiply both sides by 0, or else the equation's not going to be That's not going to work. You're not going to have an equivalent equation. And so this implies that, well, yeah, we can do this, but y can't be equal to 0. Okay, now, do you need to, every time you do this, multiply an equation or by both sides by something, or divide both sides of an equation by something? Do you need to indicate what the variable can't be? Well, for non-math majors, the way I'm going to say we should approach this is you don't necessarily have to write this out like this. The only thing you're going to need to do is you're going to need to remember every time you do something like this, it's just an indication that, okay, when I'm done, when I get my final solution, I'm going to need to go back and check my answers and plug them back into the original equation. Even if I didn't make any math errors, I'm still going to need to go check my answers to see if they're actually answers. That's all that this means whenever you do this. When you multiply or divide both sides of an equation by something that could be 0 for certain values of the variable, that's just an indication, okay, I need to go check my final answers when I'm done. Okay, another way you can look at this is that if you look at the original equation, and because this is what we're trying to solve, right? Not any intermediate equation, the original equation. If you look at the original equation, and when I say this is what we're trying to solve, because we get solutions and you check your solutions, you can plug them back into the original equation. This is what it's all about, the original equation. If you see that there's variables that obviously can't be solutions because of, like, you can't divide by 0, or you can't, for sometimes we're working with cases where we're not dealing with imaginary numbers. Well, if you have an even indexed radical, you can't input anything negative inside the radical, or you can't have a negative number inside of a logarithm, right? Something like that. Then that means you're gonna have to check your solutions. That's kind of two ways of looking at it. If you can see from the equation there's certain values of the variable that are not allowed here, then you're gonna have to check your solutions. Or if you do something like multiply or divide a variable expression by both sides, that just means we're not going to say that as non-math majors, we're not going to say that we have to be diligent about noting every restriction. That's just going to mean, okay, I have to check my solutions when I do something like this. That's what you need to note. Okay. So, all right, but now let's clear the fractions. So we're going to get y minus 7 is equal to, then 2 times 5 is 10, and now we're left with just a linear equation and one variable. So let's add 7 to both sides. Okay, y is equal to 17. Now again, with a linear equation that we worked in the previous video, the linear equations, if you didn't make any math errors, this was the solution. You're done. It's good practice to check your answers, just to check, but technically, if you didn't make any math errors, you're done. In this case, no, you have to check. This might not be a solution. Okay, but now here we can see that this is not the restricted variable. It's not 0, but if we didn't even note this, we can look at the equation and see, okay, the restriction is that you can't divide by 0. This is not 0, so that's going to be the answer. This is going to check out. But we can go ahead and verify and actually plug it in as well. So 1/2 minus 2 times 17 is 34. Okay, multiply this by 17 over 17. We get 17 over 34 minus 7 over 34. Okay, so 10 over 34. So, and there we go. Okay. So let's go ahead and multiply this entire equation by the least common denominator of all the fractions to clear the fractions, so we can see we want to multiply by 4w. So we've got w plus 3 plus 4w is equal to 4 times w minus 5. Okay, so 5w plus 3 is equal to 4w minus 20. Okay, now let's subtract 4w from both sides, and we've got w plus 3 is equal to minus 20. Now subtract 3 from both sides, and we've got w is equal to minus 23. Okay, now we could see here that it was at this point, we couldn't multiply, W couldn't be 0. And we can see in the original equation that if we plug this back in, W, we're not going to have any restrictions here. We're not going to be dividing by 0 or anything. So this is going to check out. Okay, so let's multiply this entire equation by the least common denominator to clear the fractions. So it's going to be 4 times c minus 3. And so we can see that c is not going to be able to be equal to 3. But we could see that from the equation itself. C can't be 3. You can't divide by 0. So, okay, we get 4c is equal to 12 minus 3 times c minus 3. So 4c is equal to 12 minus 3c plus 9. We can add 3c to both sides, and we get 7c is equal to 21. Divide both sides by 7. C is equal to 3. Okay, but if we come back, again, C can't be 3, or we can see here, we just can't divide. We can't have C be equal to 3 because this isn't a solution, right? Remember, a solution to an equation is you plug the value of the variable into the equation, and you simplify the left side, get a number. You simplify the right side, you get a number, and those two numbers are equal. Well, okay, let's plug 3 in. You get 3 divided by 0. That's not a number. So it's not a solution. Okay, so this isn't a solution, so there's no solution. This is you call this a contradiction, right? Okay, here, yeah, so here's an example. This is still a rational equation, right? So it's t to the second power. That's fine. You could have a variable to any whole number power in a denominator. We call it rational. But to see what the least common denominator is, let's go ahead and factor this. This is a difference of 2 squares. Now we can more clearly see what the least common denominator is. So it's going to be t minus 1 times t plus 1. And so we can see that, yeah, t is not going to be able to be equal to 1 or minus 1. So we have t plus 1 is equal to 3. Let's subtract 1 from both sides, and we've got t is equal to 2. Okay, but we see this is 2 is not 1 or minus 1. So we could plug it back into the original equation without any issues. So 1 over 1 is equal to, and then 2 squared is 4. So this is 3 over 3, so 1 is equal to 1. See? Okay, we can factor this. This is a difference of 2 squares. Okay, now we've got, so let's multiply by x plus 5 times x minus 5. So we have 2 times x plus 5 minus x minus 5 is equal to 11. So 2x plus 10 minus x plus 5 is equal to 11. So 2x minus x is x. 5 plus 10 is 15 is equal to 11. Subtract 15 from both sides, and we've got x is equal to minus 4. And we can see that's going to check out. That's not 5, it's not minus 5, so we're good. Now, just note that there's going to be 2 scenarios where we're going to have to check our solutions, and we'll learn about the second scenario later. This scenario is just, is there a restriction in the original equation, like dividing by 0? That's the only issue here. There's going to be other issues where if we have to like take both sides of an equation to an even power, it could be the case that you plug the original, the final answer back in, and there's actually, you are able to simplify and get numbers, but it's still not a solution in that case. It's not always just, oh, you plug it back in and it's like a restriction. You can't divide by 0, or you can't put a negative inside of an even radical. But for rational equations, that is the only possibility, that you just have to check if Okay, am I dividing by 0 or not? If did I get a solution? And I didn't make any math errors. So yeah, I mean, it's always good to check no matter what, just in case you made math errors. Like if this was a real life problem and I was actually really trying to, this is like for a real scenario, I would go ahead and check the solution. Why not? Just to make sure. But I'm just saying in general, if you didn't make any math errors, then when it comes to a rational equation, you're only checking to see, okay, look, am I dividing by 0 with this or not? If you're not, then it's going to be a solution. Okay, same idea. Let's go ahead and factor this here. So yeah, I think I might have said that we were only working problems. At the beginning of this video, I said we were only working problems that had variables in the denominators raised to the power of 1. So obviously that's not correct, but we're only working problems where after we clear the denominators, what we're left with is a linear equation. Later, we're going to work problems where we clear the denominators and we're left with like a quadratic equation, for example, where we're left with in the end something like this. But for all of these problems, we just end up with a linear equation after we clear the fractions. So, okay, here we've got, let's see, x. So minus 4 plus 3. Okay, is equal to, okay. So let's multiply by x minus 4 times x plus 3. So minus 14 minus x plus 3 is equal to 2 times x minus 4. So minus 14 minus x minus 3 is equal to 2x minus 8. Minus 14 minus 3 is minus 17. Okay, now let's subtract 2x from both sides. Okay, now let's add 17 to both sides. Okay, so x is equal to minus 3. Okay, but we can see that's not going to check out, so there's no solution here. Okay, let's factor each of these denominators so we can get a better sense of what the least common denominator needs to be. So, okay, we've got okay, let's see. Okay, so now we can see the least common denominator is x plus 2 times x plus 1 times x minus 1. So, or no, times x minus 2. So x plus 2, x minus 2, and x plus 1. So we've got 5 times x plus 2 minus 2 times x plus 1 is equal to 4 times x minus 2. So, okay, 5x plus 10 minus 2x minus 2 is equal to 4x minus 8. Okay, 3x plus 8 is equal to 4x minus 8. Okay, now if we add, or let's subtract 4x from both sides, we get minus x plus 8 is equal to minus 8. Now if we subtract 8 from both sides, okay, now multiply both sides by minus 1, you get x is equal to 16. And this is not minus 2, it's not 2, it's not minus 1. Okay, let's factor this here we've got okay, plus 4 minus 2. Okay, now let's see. M minus 2, M plus 4. Okay. So we've got, there we go. So 5M plus 20 is equal to 3M minus 2M plus 4. So 5M plus 20 is equal to M plus 4. Now let's subtract M from both sides. 4M plus 20 is equal to 4. Now let's subtract 20 from both sides. We've got 4M is equal to minus 16. So M is equal to minus 4, but this doesn't check out. So there's no solution here. Okay, let's see. Can we factor this? So minus 6. 3 times minus 2 is minus 6. So we can do 3x squared. Let's do minus 6x plus x minus 2. Okay, so factor out of 3x here. We've got x minus 2 plus x minus 2. So we get x minus 2 times 3x plus 1. So, okay, x minus 2, 3x plus 1. Okay. And then here, let's change this to x minus 2 like that, right? Okay. So now let's multiply by x minus 2 times 3x plus 1. Okay, so we've got 5x minus, and then x minus 2, and then minus 3 times 3x plus 1. Okay, 5x minus x plus 2 is equal to minus 9x minus 3. So 4x plus 2 is equal to minus 9x minus 3. So now let's add 9x to both sides. And we've got 13x plus 2 is equal to minus 3. Subtract 2 from both sides. So 13x is equal to minus 5. So now divide both sides by 13. And we've got x is equal to minus 5/13. And that checks out. We see that x just couldn't be minus 1/3 or 2.